Introduction to Nondestructive Examination, Magnetical Particle Testing, Module 12, Gary A. Pace, P.E., CWI, Welding Engineer, Katy, Texas. So when we're talking about a magnetic field, the term is used to describe the volume within and surrounding either a magnetized part or the current carrying conductor wherein a magnetic force is exerted. That's a magnetic field. So you can see these little lines, and I'm sure we've all seen this when we were kids. You put a magnet under a piece of paper and you sprinkle some iron powder on it, and you're going to have these lines show up, these lines of these magnetic field lines. So ferromagnetic materials, for the most part, and I'm just giving you a rough overview, but chrome, iron, and nickel are our three materials if we look at the periodic table. And ferromagnetic, this is a term that we use for a material which exhibits both magnetic hysteresis and saturation. I'm not going to dive too deep into those. And also the magnetic permeability is dependent on the magnetizing force present. But ferromagnetic means we can magnetize the material. Aluminum, copper, those we can't. The big one here is iron. Magnetic particle testing, we're only going to do ferromagnetic materials. We previously talked about dipenetrant testing, and there we could use it on all types of materials. Here we can't. We can only use it on ferromagnetic materials. If we can stick a magnet to it, it'll work. If we can't, it's not going to work, this process. Principles and theories of magnetical particle inspection. So mag particle inspection is most effective for detection of surface or near surface flaws in welds and other surfaces that we might want to inspect. It's basically a form of visual inspection, but we're using magnetism to help us find flaws, defects, and discontinuities in the surface of a ferromagnetic material. You know, if we're trying to do aluminum or some other material like copper or a material that we can't induce magnetism into, austenitic stainless steels, which are non-magnetic, this isn't going to work. The key is here, we're going to magnetize the piece and then we're going to throw some really finely ground iron powder onto the defect, and then if there's a defect that's there or a flaw or a discontinuity, it should appear. So the principles of magnetization. When parts are made of ferrous materials such as iron and we put them in a strong magnetic field or have an electric current flowing through them, then they can become magnetized. They're going to have a magnetic field. Well, once we get that magnetic field, we can use that to our benefit and figure out where there's flaws are by sprinkling iron powder on it. And so the degree of magnetization is affected by the strength of the magnetizing field or the amount of current we're sending through it. So how big is our magnetic field, or how much electric current are we sending through the part? That's going to tell us how magnetized the part is. So one of the keys here is a leakage field. We're talking about flux leakage. So when the surface or near surface discontinuity, when we have some break in the surface, it's also going to disrupt the magnetic field of the part that we've just magnetized. And then some of the field is going to be forced into the air above the discontinuity, resulting in what we call a leakage field. And once again, when we sprinkle our magnetic dust on there, our iron dust onto the part, the leakage field is where the magnetism is going to cause our dust to accumulate, and it's going to show us the flaws. The size and strength of the leakage field is going to depend on the size and proximity of the discontinuity to the magnetic field. So it depends on where it's located, the size and proximity of the discontinuity. Key words: how big is the discontinuity, and then the proximity of the discontinuity to the magnetic field. Is it flowing in the right direction, basically? We'll talk about that here in a bit. The discontinuity is detected by the use of a finely divided iron particle. So we're going to put that on the surface of the part, and those iron particles are going to show up in that leakage field, in that flux leakage. The particles are going to indicate the presence and location of a discontinuity. So if there's some kind of discontinuity, flaw, or defect, the iron powder is going to show up there, and it's going to show us where the crack is or whatever other defect happens to be in that. So a magnetic leakage field, the magnetic field outside of the part resulting from the presence of a discontinuity or a change in the magnetic permeability or a change in the part's cross section. So you can see here where we've got our little notch cut in the part, and it's causing our magnetic field to circumvent that location. And then when we put our iron powder on there, those particles are going to accumulate in that magnetic leakage field. So when we have a horseshoe magnet, a little theory here, we've got a horseshoe magnet, and you can see that we've got our magnetic field flowing in one side and out the other on the north and the south, right? So like a bar magnet, it's going to be a permanent magnet, and it's going to have residual magnetism, and it's going to attract iron filings to the ends where the leakage field occurs, right? If we sprinkle magnetic iron particles on the parts of the horseshoe magnet where there isn't the N and the S on the curved part, nothing's going to stick there. The only place where the iron particles are going to show up is on the poles there down at the end. And so those ends are commonly called north and south poles, indicated by a north and south, but that's where our iron filings are going to end up because that's where our leakage field is. When we have a continuous ring, the ends of the magnet are fused or welded into a continuous ring as shown here. The magnet will no longer attract or hold exterior magnetic materials. This is because the north and the south pole no longer exist. Thus, the leakage field does not exist. So if we take that magnet and we weld it together, the north and the south pole, this is what it's going to look like, and we're not going to have a place to pick up. We're no longer going to have a north or a south pole, and we're not going to have a leakage field, so we can't pick up the iron filings. So in this case, the magnetic field is going to remain as shown by the arrows, but no iron filings are attracted.